right? This part, okay, is going to be what the tool is seeing over here, right? The two dots I've drawn now. If you have low B and N, okay, so we have low B and N, the hardness you're going to see is somewhere around here. Okay, so this is for low B and N. So it is very not so much difference from your bulk hardness, yes or no, right? The difference is so small, right? If you look at hardness, this is the delta, right? This is the delta, hardness delta, right? The or hardness delta. Okay, so the difference in hardness. Now, if you have high B and N, can you see what will happen? This is for high B and N. The tool will hit on a surface that, so if you look at this, right? This is your delta H now, right? The hardness can be twice, right? It can be twice. Now, so question for you guys, right? If you were to take the same hardness or same undeformed chip thickness 0.03, what's going to happen with the high B and N? Anyone? What's going to happen? It's going to hit a very higher what? Hardness. Yes or no? This is hardness. So what is the solution? Anyone? Do you go smaller undeformed chip thickness or you go bigger? Anyone? Hello? So what we will tend to do, okay, is we go higher. So let's say if we take 0.1, so this over here, this point over here is 0.1 millimeters. When you take 0.1 millimeters, what happened down here is the hardness, delta H, has been what? Reduced. Okay, the delta H has been reduced. So that is why, it comes back to over here, that is why when you have a material with high B and N, right, you don't go less, you go more. Okay, I have difficulty grasping this concept until I start sitting down and think about this aspect. Okay, we always think like, okay, if you bite something that is very hard, we're all human, we all think about food, right? If you bite something very hard, right, you will reduce your bite. But on this case, I'm telling you, go opposite, bite more. You see where I'm coming from? And only with knowledge like this, then you are convinced why you should bite more, right? Because when you bite more, the hardness reduces. Okay, so this is a very interesting aspect. Okay, that's why with knowledge you tend to do things opposite. Okay, and I faced a lot of problem. I was in a aerospace company giving consulting, and they have exact this problem, and I told them, come on, go more. They give me a dirty look. They say like, hey, Sunshine, are you crazy? Okay, I keep on telling them, go more, go more, go more, and guess what? It works. Okay, and then when it works, look, I don't have any rings with me. Okay, I don't have any rings, so I'm an engineer, like you guys will be engineers. I don't have any rings. Okay, so I don't put on my rings because I don't want barrier. But when you go out to consult, okay, is your knowledge that prove how good you are, and nothing to do with the rings. Okay, so there you go. So with that further away from the, okay, so with the depth, okay, with that further away from the newly generated surface, okay, the hardness will recover, right? Will recover back to its initial value. right? So the hardness will go back to its what? The hardness will go back to its initial value. However, the recovery depth, right? The recovery depth is dependent on B and N. Okay, it's recovering. So high B and N will have higher recovery depth. Okay. Okay, so the recovery depth is dependent on what? B and N. Okay, so the recovery depth is further away, right? When your B and N is very high. Okay, so that is why we have to take what? We have to take a bigger depth with high B and N. Low B and N does not matter at all. Okay, now let's look at another aspect is the effect. Okay, so is the effect of strain hardening on cutter path during milling. Okay, so we are looking. So what do I mean by milling? Okay, so in milling, this is my workpiece. You can YouTube milling. Okay, later on after my class you can YouTube milling. So in milling, what will happen is you have a tool, right? So this is what I call my tool holder, right? So over here, right? What we have, so this is known as the tool or insert, right? And if this is our neutral axis, right, this thing will rotate. Okay, so that is our rotation. Okay, and then we have our work. So this thing can go. So if I were to draw our transformation, right? So this is our X, Y, and Z, right? The tool can move up and down in the Y direction. Okay, it will go up and down, up and down. And the workpiece, right? So this is our workpiece. So the workpiece can move in the X direction, or it can move in the Z direction, or it can move in the X and Z direction. Okay, so this motion X and Z direction, the speed is about is between one, you can go between 1,000 or 1 meter per minute and up to like 5 meters per minute, right? The velocity over here, the rotation over here, when we convert to linear velocity, right? The linear velocity over here for the tool rotating, it can be between 150 and it can go up to 500 meters per minute. So I'm writing this down so you can see the, oh God, you can't see this. I do apologize. So the workpiece motion, right, is between 1 meter per minute to 5 meters per minute. Okay. Whereas the tool, when it rotates, when you convert to linear velocity, is 150 to 500 meters per minute. That's where I'm giving you to, I'm wanting you to see the relative velocity. Okay. Right. So bearing in mind what we have drawn down here, okay, high B and N means you have to take deeper depth of cut, right? So in milling, as what you can see down here. So in milling, the tool is rotating. Right, the tool is rotating, and the workpiece material is under linear motion. Okay, the linear motion is in X and Y direction. Sorry, it's in X and Z direction. So it's in your X and in your Z direction, right? So there are two types of milling configuration. Okay? So there are two types of milling configuration. Okay, so there are we have what we call down milling. And down milling is also climb milling. I know, it's English. I know, okay? But remember, down milling is also known as climb milling. B, the next one is up milling. And we call it conventional milling. Okay, we call it conventional milling. So when you have B and N values, okay, again, we look at B and N. Now, why am I teaching this? Okay, I've been asked a lot of times this question, what to use, okay? So, and sometimes when you tell your client what to use, they are very resistant. Okay, so that's where you have to explain. I have to explain all this. Okay, so if you look at B and N value, right? So you have low and high, right? Now, the whether up or down milling has to be used will affect your cutter path. Okay, that's why I'm so the whether up and down, these two, right, will influence cutter path. Okay, and later we'll see how you influence cutter path. Okay, so with over here we have milling configuration. If it's low B and N, you can use up or down milling. Does not matter. Okay. However, when you have high B and N, right, you have to use down milling. You have to use down milling. So what do I mean by down milling? Okay, what do I mean by, and why down milling is also known as climb milling? Okay. So I'm going to teach you the characteristic of down milling. And by the way, when you do cutter path planning, okay, plan how the tool is going to move, right? No doubt there are software to help you to do that, okay, but the software is dependent on how good the user is, okay, how good. So the software will not know whether it is high B or N, okay. You have to be competent enough to know that, hey, you have to use down milling. Why? Because it is very strain hardening sensitive. So let's look at down milling. All right, let's look at down milling. So I'm going to draw down milling, okay, and I'm going to deliberately draw it very big, okay. So this is your tool.
Makes me uncomfortable.
Okay, so that is your 2 now. Down mailing is when this happen.